So now we can just plug it right into our equation. And we can say that the voltage across that capacitor is going to be equal to VC of infinity, which we said is 9, plus VC at 0, which is 0 minus 9. So instead of saying a plus, I'll say minus, minus 9 e to the minus t over tau, but tau is 1. So that's just the same as saying this.
So
our units are volts, and now we can say that is our answer for part 4. And just hold your question for a second. I just want to finish up the problem and we'll take questions. And the 5th problem is to find what you're asked to find. Well, I'm asking you to find VC naught, so that's done. Okay. Your question?
Well, I was gonna ask, like, would we stop here, or like if we're given like a t at a certain time, then we would plug in t and find the actual voltage at that time?
You're probably not going to be asked to find the voltage at 7.623 seconds. You're probably just going to be simply asked to find the voltage, period. So this is a break from circuits 1, where your answers were a number. Your answers in circuits 1 was 7 volts or 3.2 amps. In circuits 2, it's going to be functions in time usually. But now let's draw what this thing looks like. Let's see, Caleb, where does this start? What's the start voltage of this at time equals 0? When you plug in 0 for t, what do you get?
You get 0 volts because, E becomes 1 because anything to the power of 0 is 1.
Perfect.
And so 9 minus 9 is 0.
Exactly. That's the exact right thing. Looking at this thing, 9 minus 9 is 0. Another way you could have said it is that we already figured out what VC naught is. It's equal to 0. Both things are true. And Caleb, just finishing you up after a long time, what's this voltage? For t equals 100, 1,000. What does this part become for big T?
Because it's big.
Well, no, e to the minus t is equal to 1 over e to the positive t.
Yes. So it becomes smaller.
So e to the positive t becomes just ridiculously huge. So 1 over something ridiculously huge becomes
small.
Becomes small.
Very small.
And so what does this whole thing become? If this right section becomes really small, what does the whole thing become?
Closer and closer to 9.
Closer and closer to 9. So it looks like this, where it's sort of asymptotically approaching 9 volts after a long time. And after one time constant, it will get within about 30-ish% of the final value. So, this looks to me like about a third of the way up. So this is one time constant, which is 1 second. And then after 5 time constants, we could draw it all the way out here. After 5 seconds, it would get within 99% of the final value. Okay. So that is what it looks like. Now,
Colonel Squire?
Yeah.
How would you adjust the time that delay in a circuit if you were going to use practical application?
Yeah. So let's say you wanted to make it not something that had a 1 second time delay, but had a 10-second time delay. What component would you change to increase the time constant by a factor of 10? Over here on our left, there's our time constant. What would you change?
The size of the capacitor?
Yeah, you could make the capacitor 10 times bigger, and then it would take 10 times longer to come to a final value. What else could you change?
The resistance.
Yeah, make it a 1 mega ohm, and then that would also make it 10 times longer. Now, what if I'd asked for something else? What if my step 5 wasn't just you're done? What if I had asked, hey, what is this I sub C? What would your 5th step be then?
You can plug it into the equation, right?
What equation?
I equals CV.
Yeah, you got it. IC is equal to C dVt. So you could instead, if I had asked that, you just multiply the derivative of this by C. So that would be 10 micros times the derivative of this thing. What's the derivative, DJ, what's the derivative of this constant 9?
0.
And what's the derivative of this thing?
Become positive 9 e to the minus t.
You got it. E to the minus t. And so therefore, I would say that whole thing is 90 e to the minus t microamps. See how beautiful it is when we use these engineering notations? And you'd be done just that fast.